So today we're going to be talking about similarity as explored through dilations. So to warm us up, we've got these two questions here that we would like you to pause the video and then come back when you've finished them. Alright, so in this first one, they want us to translate that given C 4 units to the right and 2 units up. So if you'll recall, a translation is just a slide, a movement. It shouldn't impact the size or the shape. So if I simply slide this 1, 2, 3, 4 to the right and 1, 2 up, this is now my image. And then I'm going to answer these questions. Is the image the same shape? Yeah, they are both C's. Is the image the same size? Well, I mean, I think so. I can just verify by tracing it back on. And yeah, they are the same size. So yes. And then I'm going to go a step further and say, well, because it was a rigid motion, right? Translation falls under that category of rigid motions. It's not changing size or shape. Now, in number 2, they want you to do a dilation with a scale factor of 3. So, you should have sketched it. It's going to be something that's bigger, specifically 3 times the size. So if I'm doing a dilation of 3, 8 times my scale factor of 3 is going to be 24. And 6 times my scale factor of 3 is going to give me 18. So that's information I can put in the picture. Can't necessarily do anything else. And now I'm going to answer these questions. Is the image the same shape? Yes. It is still a C shape. Is it the same size? Absolutely not. No. It got larger. Okay. And right here in the beginning, this is an example of congruence in number 1, meaning it is the same shape and the same size. And then this is an example of similar. It is the same shape, but is not the same size. And if you could you just take a minute, pause, and read this kind of like blurb here? And I've highlighted some important stuff. And then come back when you've finished reading it. Okay, so one of the most important things in this little blurb is that an important aspect of dilation is that the shape does not change. All right, size, they're going to say may change. For us, we're just going to say size changes. We'll deal with this may thing later. Well, why not? Why don't we deal with it now? If you do a dilation of 1, size doesn't change, and technically they're similar because you did a dilation. There's lots of other reasons too, but that's an example of this may change. The most important thing is this proportionally. The lengths change proportionally. And we might not know what that means right now, but the idea is it's not changing randomly. Everything is changing according to some order, according to some scale factor. And it's not like one side's changing at a scale factor of 2 and another's changing at something different. It's not a different rate. All the sides are changing according to this scale factor, that is, proportionally. And they kind of say that down here. Similar figures have the same shape, but not the same size. All right? And the way similar figures are created is through a dilation. That is, they're created by multiplying each side by the same number, and we call that a scale factor. When you multiply something by the same number, that's proportionality. Okay? So the real world example that they're using here is these puppies. And here you have the original, and it's basically saying, if you put it on a copier, you could, shrink it 50%. That's multiplied by half. But at least in this picture, something's happening. Something's occurring to this original to get it to the enlarged. And it's a scale factor. Could you figure out what the dilation is? So pause it. Take a second if you already know. Great. And a lot of you figured out, well, if I just pass that side of 5 through a dilation of 3, I'm going to get 15. Okay? But there's this next question. What is a ratio? And a ratio is a fraction, simply put. And it's comparing two things, specifically using division. So we can use this idea of a ratio, to figure out scale factor. What scale factor was used to enlarge the puppy shown to the right? I know you can just guess and check. You can do 5 times 3. But what's interesting is, with a little bit more like difficult scale factors, you can always take the image that is the enlarged, or the result, take that number and put it on top. And then compare it to your original side. Put that in the bottom. And when you do that math, when you compare the image to the original in a ratio, it spits out the scale factor. This tells you my scale factor was 3. Okay? That's one of the values of a ratio. Because 3 affected my original side to give me my image. Okay? We're going to flip it over, go to the investigation. You're going to pause the video now and kind of try this out. And if you need a little hint, when they say verify that her ratios are equal, they're talking about these numbers here. We're talking about those numbers there, and it looks like I forgot that. Okay, so just verify that these two ratios are the same. Or, I don't know. Go as far as you want and then come back to the video and we'll just kind of talk all of this out. I think we're going to do all of investigation 1, which is this A, this B, and this C. And you can pause it and come back whenever you feel it's necessary. Alright, so the first thing, verify that her ratios are equal. So I'm going to talk about the heights. She's saying that it's 24 over 8. And notice what she's doing is she's taking a big side and comparing it to a little side. Like, these sides correspond. They are the heights, right? They match. So this ratio, remember, ratio is a fraction. It can be computed. It has a value. I don't know what it is, but 24 divided 8 is apparently 3. Okay? And if we think of this as image, and this is original, that is a potential scale factor. All right? And I say potential because if the scale factor really was 3, then this ratio, the ratio of the widths, needs to be the same. So that's the value of looking at these ratios and checking if they're equal. Because if they're equal, if 18 divide 3, if 18 divide 6 is 3, as it is, that's telling me my height and width changed, that magic word, proportionally. They were dilated by a scale factor of 3. And that's like the crux of similarity. And we're going to use this information in like C. You'll see how it's applied. This is just getting you to see that this pattern exists. Another way to look at this is Casey's brother, apparently. Casey's brother wrote this. And now, Casey's not comparing big height to little height. Casey's comparing something from the big figure to something from the big figure. So the ratio on the right is a big divided by a big, and the ratio on the left is something from the little figure divided by the corresponding piece from the little figure. And notice it's like the big height divided by the big width. And then it's the little height divided by the little width. That matters. He didn't mix and match. And you can test out this. This is actually called a proportion. And you can test it out one of two ways. You could simply take 8 over 6 and check what that equals. 8 over 6 is apparently 1 1/3. So 1.33 repeating. And I expect 24 over 8 will be, 24 over 18 will be the same thing. And if we check it out, 24 divide 18 is the same thing. This is more evidence of proportionality. So you could just divide them. Another way you could check that they're equal is cross multiply, or what I'm going to call this, like crisscross multiplying or butterfly multiplying, whatever you want to call it. I guess I'll clear up this page and I'll bring this to the top. Whenever you have this kind of a setup that is a fraction equal to a fraction, you're allowed to do this crisscross multiplying. And you're going to take those two numbers and multiply them. And then write the product, the result, down here. And then carry down that equal sign. And then check the other product. 6 times 24. And if those things are equal, that is evidence of proportionality. That's another way to verify that this ratio does in fact equal the other ratio. They are equivalent. Now, this is the next thing we do is how to apply it. It's like, okay, she wants to enlarge the original. Now, when we enlarge it, that's a dilation. Okay? And dilations always produce similar figures. Alright? Similar figures are proportional. They have that property. So, because she's enlarging it, and because I know that this image will be proportional, will be similar, I'm allowed to make a proportion. I'm allowed to take these numbers and then put them in equivalent ratios. And this is valuable because I can say, let me take this little height of 8, and I'm going to compare it to the corresponding bigger height of 20. Okay? I'm going to repeat this pattern. Now I'm going to take the little width, and I'm going to compare that to the big width. And this is where it's valuable. Now I've got 6, and I've got an unknown. And so long as I'm consistent in how I make this proportion, I don't mix and match. I didn't like swap the 6 and the 7. I didn't like do the width with the height. I didn't mix it up. I did the little height with the big height, and then I did the little width with the big width. Even though I don't know it, I know it belongs to the image, to the bigger shape. So it's like little on top and big on bottom. Alright, this is a valid proportion. Now I can use math, I can use that crisscross multiplying to solve for my variable. Because when I do this, now it's not just a number, it's a variable. So I have 8x equals whatever 20 times 6 is. It's probably 120. I don't know. Yeah, it's 120. And then we use algebra and divide by 8, and x is going to equal, my suspicion is 15. Maybe. Yeah, it is 15. And how I subtly did that was another method. Okay, this proportion also works, but remember how like we started off with this idea of are these ratios equal, right? I have 24/3. That tells me my scale factor. Well then, you know, the other fraction, 18/6, needed to be the same scale factor. I can use that here. I can take my original height of 20 and compare it, divide it, make a ratio with my, take my image height and compare it to my original. And that will guarantee tell me the scale factor. That will tell me how it's transforming. So 20 divide 8 tells me it's 2.5. The scale factor is 2.5. This is what the width needs to be multiplied by to give me the image width. So if I do 6 times 2.5, that's how I get 15. So this unit of similarity, of proportionality, of dilations, there's just too many different ways to solve a problem. I've shown you like 2 or 3 here, and you're only going to learn more. So everything you do, just be careful and trust that you're doing it properly. So long as you show your work, I trust that you're going to get the correct solution, even though our work may look different. So I would take this time, pause the video, and try investigation 2, which is basically the back of the page. And I've kind of given you a little hint here. All right, let's see where we are. All right, halfway. Okay, so if you've come back, let's read this. It says, assume one triangle has side lengths 6, 7, and 10. Okay? And then the other triangle has side lengths 3, 4, and 5. Now they're not telling us they're similar. Now they're not saying we enlarged it. Right? When I hear enlarge, that guarantees me similarity. That guarantees me proportionality. This is the other way. This is like, yo, something happened. You have these two shapes. They want to know, are these triangles similar? Did a dilation take place? Well, if a dilation took place, then all ratios will be equal. All right? It will look like this original problem where, you had a ratio of heights and a ratio of widths, and they were equal. That should happen with every single side in these triangles. It has to be all of them. They all have to get affected by the scale factor. They all have to have the same multiplier, the same scale factor. When they have that, that's called proportionality, that everything changes the same way. Okay? And that's how we'll decide if they're similar or if they're not. So I can tell that these are the big numbers. That's going to belong to the, what I'll call the large triangle. These are the little numbers. They're going to belong to the little. And I've gone one step further, and I've kind of ordered the sides. I can see the side at the bottom is the biggest. I think that this side over here is the smallest in terms of, the 3 sides of this triangle. That red one is clearly bigger than the green. And I think this blue side is the medium length. And the reason why I'm doing that is, now I can say, out of these numbers, 10 clearly belongs with the big side. And then I go the other way. I then go to the smallest number. That's easy for me to see. That's the smallest side. So whatever number's in the middle left, and whatever side I didn't assign yet, that's the medium side. We can apply this logic again over here. The big side is that 5, so that 5 needs to go down here. The little side is the 3, so that's going to go on this. And then the side in the middle is that 4. And now I'm going to create ratios. I'm going to check. I'm going to do the big side divided by the big side. So it'll be 10 divided by 5. I can tell that's 2. I'm going to do the small side divided by the small. 6 divided by 3. Oh my god, that's 2. Aren't they similar? They must be, right? The equal ratios. No. Because the last side, 7 divide 4, that is not 2. I don't know what it is, but I can promise you it's not 2. It should be 8. 7 divide 4 is 1.75. This right here is evidence that the answer is they are not similar. Are these triangles similar? No. They are not similar because the sides, and you could say this a ton of different ways, the sides do not have the same scale factor. Okay. You could also say the sides are not in proportion. You could say the sides do not grow at the same ratio. You could say the ratio of the sides are not all the same. There's just too many different ways you can say it. As long as you say something logical and you show your work that there is this disagreement, that's evidence. Now in B, they are promising you that they are similar. They are promising you that some dilation took place. So I'm not going to do a proportion because there's, this side I got to find and this width I got to find. That would be a lot of work. That would be 2 proportions. I'd have to have a proportion for x, right? And then I'd have to have another proportion for like y. So instead, I'm going to do this scale factor method. I'm going to do the ratio. I'm going to say, okay, this is my image. This is my original. I know if I take something from the image, right, 24, and I divide it by the corresponding side, 8, that will tell me what happened. You can see that in the first set of notes, right? You can always figure out the scale factor by taking the image and dividing it by the corresponding side in the original. That's what I'm doing here. I'm finding out that my scale factor is the result of 24 divided 8. It's 3. So if this is my scale factor, I am supposed to take 11 and times it by 3 to figure out that this side is 33. Now, it's like, what number, y, times 3 gives me 18? I've actually made an equation. I've actually said 3 times this side is 18. I can divide both sides by 3 and figure out that y is, what, 6? 6. And when you want to go the other way, you can just divide by the scale factor, or you can multiply by the reciprocal of 3 over 1. You can multiply by 1/3. Okay, that is division. And then I'm going to let you do this. I'm going to let you read this reflection and kind of write your notes. I'm not going to respond to that. If you want to talk to me about that, you can ask me in class. We are at 23 minutes. It's not too bad. Let's let you do the rest of this practice and that reflection. And I guess what I'll do is I'll do one of these. Sure. One of these, and I'll do 2 of these. I'll do this one, and I'll do this one. Actually, no, I'll do 8. Okay. So pause the video, do everything, and we'll come back. Okay. So in number 1, it's telling you solve the proportion. Proportion is a fraction equal to a fraction, this setup. So all we got to do is cross multiply. You'll get 2b equals, what, 36? Divide both sides by 2. b equals 18. So apply that logic to number 1 if you need. In 3 through 6, they promise you that the shapes are similar. And they're saying find the missing side using whatever you learn. It could be a ratio or proportion. Just make sure you're using corresponding sides and I'm saying you should highlight or trace to see this more clearly. Specifically, 6 is where that gets tricky, because this side, what does it correspond to? Well, it corresponds, you know, it's opposite that little corner thing. So I can see that that 10 really corresponds to that 5. And that's as far of a hint I'll give you for 6. For number 5, we're interested in this unknown, which I'll call x, and I see that that matches 21. And then I can also see that my base of 10 matches my base of 15. So I always like to do the big over the little equals the big over the little. I like proportions. To me, they're just easier to do. 10 times 21 is 210. 15 times x is 15x. Divide both sides by 15. And x is, I got no idea. 210 divide 15. 14. Boom. That side is 14. I challenge you, tell me what the scale factor is. That would be interesting. Spoiler, it's a decimal, I think. Okay, now, this is like a continuation of number 1 and 2. I'm warming you up with 7. Alright, it's still that idea of this entire number times that entire number, 6. It's going to be equal to this entire number times that entire number, 6x. Alright, divide by 6, divide by 6, x equals 1. And now I'm using parentheses because p plus 8 is just one number. It's not two numbers. It's when you know the value of p, it's one number. But right now we don't know it. But we're still going to slap some parentheses around it and treat it as one number. Because when I do this multiplication, I'll get 3 times p plus 8 must be equal to whatever 5 times 6 is. 5 times 6. And I'm showing it to you this way because 5 times 6 is very obvious. You can use a calculator. It's 30. But 3 times p plus 8 is different. This you need to distribute. There's 2 terms to multiply by 3. It's 3p and 3 times 8, which is, I think, 24. And now we have something slightly more complicated to solve. Now we gotta, say, what am I solving for? Well, I'm solving for p. Before I can divide, I gotta get rid of this lingering constant of 24. So now I'm gonna have 3p equals 6. Divide both sides by 3. P clearly equals 2. And I think that's enough information for you to do the rest of the lesson, to practice. I hope this was a good lesson, and I'm hoping you enjoy this. And if so, I will continue to make these videos and post them to YouTube. As always, thank you for listening, and I'll see you next time.